Okay, so it's 2 o'clock. So at our last lecture, we started looking at PID controllers, proportional integration or integral derivative controllers, PID. And we looked at proportional controllers and compared it to some of your circuit stuff you've done, particularly the op-amp. Right? Now, the next stage would be to go to proportional and integration controllers. But before we do that, we need to look at some step responses and look at modeling systems, because when we go to PI controllers and PID controllers, we start to move into second order systems, which are not so simple. So you have a system you're trying to control, but you don't know anything about it. Right? So companies employed you to control this system, so you have to design a compensator and put it in a feedback loop to give it a response that they want. But they don't know anything about their system either. So you have to come up with a model of the system. And some systems can be extremely complex and can, have sort of 5 or 6 poles in it. Do you know if anybody else is coming? Okay. Okay, so I'll start again. Last lecture, we started to look at PID controllers. A lot of you weren't here then, so hopefully you've looked at the notes. And we started to look at a proportional controller, the simplest case, and we compared it to what you know, which is essentially op-amps and how they operate. The next stage is PI controllers and PID controllers, and then we start to get into second order and higher systems. And so before we do that, we need to look at what type of responses second order systems have. So the scenario is that you're hired by some company to make the system that they use operate in a more functional way. So they might tell you that they want to have a certain rise time or sort of maximum overshoot or a certain settling time or something like that. And so your job is to design a compensator to give you that sort of response. But in order to do your design, you need to know something about the system that you're trying to control. And this is the realm of what's called system modeling or system identification. And real-life systems are extremely complex and have many, many poles, but they don't help you when you start to, even if you measured the location of every pole for a system, it's not really going to be very useful to you in order to do your design. You can use that at a later stage with some computer package, but in the beginning, you need to get a pretty good idea of how the system operates. And in terms of interpreting how they operate, if you go above second-order systems, they just get too bad to work out. So what you really want to do is try and model your system as first-order system, second. Real-life systems do not behave that way, but they can be fairly well approximated under certain conditions to be like. So the task is, okay, how do you identify the system? You want to come up with its transfer function or the Laplace transform of the system. You need to find the poles. The normal way you do this is what's called a bump test in industry. Now, you can imagine what a bump test means. You give it a bump, right, and see what happens. And so it's a step response, basically. Give it a jolt. Obviously, you don't want to hit it too hard because you might put it into an unstable state or you may exceed its design limitation, right? So you have to be very careful what sort of bump you give to your system when you're doing this sort of testing. So the best thing to do is talk to the technicians, and they'll give you a pretty good idea of what you do with the system. Okay, so we do a bump test. Now, a bump test of a first-order system has what sort of response? Well, it has a rising exponential. If it's a second-order system, what kind of response? So it might go up, overshoot, and then start ringing for a while before settling down, right? So they're the two types that we're going to look at. And once we get this step response, we measure the output. We want to relate that to poles of the system. So this slide just basically is summarizing the steps. So the simplest case is first-order systems. So first-order systems can be described by a first-order differential equation. So we have a time constant for a system, tau, or sometimes you have the exponent sigma for your system. And I think we all know the expected solution for these are basically exponent. So a linear sum of exponentials is a common solution to the first-order differential equation. If you have a forcing function, and in particular, if your forcing function is a step function, then that gives you your bump response. And the bump response for a first-order system is something like, what does this look like? I think you know pretty well that in this case, we're going up to B, and it goes up at a certain rate, and that's your step response. So how fast it goes up depends on sigma. If sigma is large, then it goes up very quickly. If sigma is small, then it goes very slowly. Or if the time constant is long, it goes up slowly. If the time constant is short, it goes up. Yeah? So yeah, okay, these are very simple systems. But how do you describe these systems? Well, there are a number of things we want to know about the response. One, of course, is the settling time. So how quickly does it get to the desired response? So you want it, let's just normalize it to 1, and you want to get it up to 1. And so you want to ask the question, okay, it's rising. How quickly does it get up to where we want it? Right? We want it to get to 1, but it'll only get to 1 after an infinite amount of time. So you ask the question, okay, do you want it to be within 14% of what you want? All right. In other words, it's risen to about 86% of final value. In that case, the settling time is 2 time constants. So after 2 time constants, which is your tau, you get within 14% of the final value. If you want to get in within 5% of the final value, so it reaches about 95%, then you need about 3 time constants. So after a time of 3 time constants, you're within 5% of the final value. Now, if you want to do better, say get within 2%, you need to go 4 time constants, and you want to get within 1%, you need to go 5. Now, different definitions of settling time depend on what percentage, and the company may actually tell you when you are contracted, what they want. Okay, so that's simple. So you need to work out what is the time constant of your system, and that'll tell you settling. Okay, the rise time. So the rise time you want to know too. Now the rise time is sort of related to tau, so you want it to go up to 1, and it's rising like this. And the question is, okay, how long does it take for the response to go from 10% to 90%? And that's the rise time. So if you do a bit of algebra, the rise time is about 2 times the time constant, 2.2. The Laplace transform, or in the Laplace domain for a first order system, is given by this. So we have a pole at minus a. And if the forcing function to the system is a step function, which is defined this way, then the Laplace transform of step function is 1 on s. So this should be just revision for you. Yeah. So this bump response or step response for your system product of 2, and then you can split that up into partial fractions. So this says that you have a pole at 0 and a pole at minus a. So once you split it up into these partial fractions, then you can relate it to the temporal response. So this term will give you the exponential term, and this term will give you the constant term. Right? So this is all revision. Yeah? All right, so that's simple. How about second order systems? So second order systems are described by a second order differential equation, and you need two coefficients, A1 and A0, in order to find the equation. And so again, you're interested in what? If we transform this differential equation into the Laplace domain, so we have a driving function R, function of time, and our output is Y, which is also a function of time. Take the Laplace transform, and we have an equation like this. Now, that doesn't really tell us very much. What we really want to know is what is the response classic behavior. And what is classic behavior? Well, if we give it a step response, so we're going up here to 1, then classic behavior will do something like go overshoot, settle back to final value. So we sort of want to know what is the frequency of this thing, and we want to know how quickly this decays. How quickly does it decay? Right? So the frequency was related to this natural frequency, and the overshoot and the damping or decay like a cubic heater. Right? So it should tell you something about how quickly it settles. So this natural frequency and the damping. This is natural frequency, and this is the damping factor. And these two terms describe time response, obviously. So the step response, what is this? Well, you have to multiply by transform the step, and you take partial fractions again. And so you need to solve for S1 and S2, which is the poles of your system. And it turns out that they're related to the natural damping rate, right? And in terms of the terms here, they're related to poles. So the solution then for a step response is it'll eventually go to some value k, and there will be an exponential term and another exponential term because of 2 poles. And the question is, are these poles real, or are they imaginary, or are they a bit both? Right, depending on what they are, respond. So there are 4 possibilities. You could have 2 distinct real poles, and this is what's called overdamp. You can have 2 real poles that are identical, and this is what we call critically damped. You can have 2 purely imaginary poles, which we call undamped. And then you could have 2 poles with real and imaginary parts. So 2 distinct poles should have an exponential-like response, right? If they're real, we expect to be sort of exponential-like. And it would depend on the relative size of S1 and S2. If we got 2 poles that are identical, then it gets a little bit more complicated. So if I draw in the Laplace domain, if we have 2 distinct poles, S1 and S2, then they're both real because they're sitting on the real line. So this is a real line, and the vertical axis is the imaginary line. And so you have 2 distinct groups. Now, you can change the poles so that this one starts to move there and this one starts to move there. And then if they both sit here, that's called damped. So you've got 2 poles sitting there. So that's critically damped. If you have the situation where undamped, you may have your 2 poles sitting like that. Got no real component. So what does that look like? Yeah, it just continues forever and ever. Yep, and that's an oscillation. So that's undamped. So that corresponds to this one. And the last one corresponds with, so they have a real and imaginary part. And the time response, that sort of thing, step on somebody doing something like that. So that's the more interesting case. So let's look at it some examples. Depends on your situation. If you don't want any overshoot, you want 2 real poles. If you can tolerate some overshoot, substitute, then you could have two real and imaginary. Okay, so let's look at the first case. Now, it might be intuitive to, so this is the transfer function. Now, that's before we solve this problem. Let's go back to the most general case in which we solved, right? So that's this, right? So what does that say? If we go back to here, then this term here is omega n squared, and this term here is omega n squared, and this term here is 2 theta times omega n. So you can, from that straight away, work out what the natural is and then get the damping. You can do that straight away. So this denominator in this equation is called the characteristic function because it determines the response. So if you try and find out what the poles are in this system, I think it's fairly straightforward that you can break this down into S plus 1 and S plus 9, right? So that says we have a pole at -1 and a pole at -9, okay? So this means we've got two real roots, and so our solution is going to be like that. So this is an overdamped system. And sigma 1 and sigma 2 are negative. So eventually it's going to reach the desired eventually. If we go to this problem, again we have omega n squared. Here is omega n squared. But now we must have changed the damping, because now before it was 10, now it's 6. So we've changed the damping. Remember that this is 2 times damping factor times the natural. So we've kept the natural frequency the same, but you've changed the damping factor. You've reduced the damping. Right? So again, you look at poles. They're real and negative, but they're both the same. So this is a critically damped system. So this is the solution. So you have a sort of exponential-like response. You also have, so depending on the size of R1, have it going up a lot all the time. Could be a contest between the linear time function and the exponent. So this is critically damped. If we go to this case, then we have omega n squared again, but we don't have the damping factor seems to be, and so you might expect that this is undamped. And sure enough, you look at poles and they're purely imaginary. Right? So we've kept omega n the same and made the damping 0, and so this thing is an undamped. So it has cosine-like function. Okay. The more general case is where we have components. So again, we have omega n squared. This part 2 is now 2. The damping factor is omega n. So omega n all this time has obviously been what? 3. Yeah. And so looking at this, in this case, what is the damping factor? Must be a third, right? Yeah. So the roots are real and imaginary. So this is an underdamped system, and so we have a step response like this: 2 poles from our system and a pole at the origin with the step, and so we have our constant term, and then we have the term. And so the solution is something like this. Yeah. Now, this stuff you don't have to remember. In the exam, you'll have an equation sheet with all this stuff. Right? In industry, probably will remember, but if you don't, use it. Okay, so step response of a second-order system. So we're going to consider some general function, and we're going to have, when B is 0, it's undamped, and so poles are purely imaginary, and so we have our natural frequency square root of C. For an underdamped system, B is not equal to 0, and so we have real and imaginary. And so we define a damping factor. Fine, this way. We've sort of already done that, find the damping factor, because what we said was that's equal to omega n squared, and this term here is equal to 2 times the damping factor omega n. So you can get the definition of the damping factor straight from the characteristic equation, right? So remembering the characteristic equation is quite. So in general, we have this description. K is the gain of the system, omega is the natural factor. So the poles occur here. So it's the half of the coefficient in front of S, and then you have the damping factor square root, and so you can put it in terms of a decay, and you can put it of an oscillation part. Right? So the actual signal, the response, the oscillation will not be the natural frequency, it'll be something. All right. A picture is always better. So if you plot the poles on the complex plane, so you have the real part on this axis and the imaginary part on this axis, and you have your 2 poles, then the radius taking from the center to the pole is omega n, your natural frequency. The imaginary part, pole, is if you're here, gives you the imaginary part, and if you go down here, gives you the real part. So you can do the algebra. So the length of this is the damping factor times omega n. So the length of this, you can use Pythagoras theorem to come to this equation. So the hypotenuse is omega n squared plus this term here squared. So this term here squared plus this term here squared is equal to omega n squared. And so you can solve. Yeah. And you can do the same down here. So this length here, you can say, well, it's this square of this plus the square of this is equal to the hypotenuse. So you can see how, okay, if I change the position of my poles, I can change the damping and I can change the oscillation. So if I move the pole, stay on the vertical axis and move the poles upwards like this, downwards down here, what happens? The oscillation frequency increases. Yeah. The damping doesn't change. Sigma doesn't change. The damping will do, sigma doesn't, right? Okay, so what if I this time go this way or this way, or this way, this way? What happens? So the damping will be different, oscillation. Okay, good. So diagrammatically, you can see in your head you shift poles around. So if you move the poles closer to the complex axis, so the imaginary axis, what do you expect to happen? The decay rate is going to be gradual, isn't it? Yeah. The sigma is getting smaller. The rate of decay is quite slow. So if you put it actually on the axis, then you don't have any decay, then you've got the oscillation. So the further you move it away from the imaginary axis, then quicker. You can still play around with the damping. If you, yeah, true. You've kept omega n the same. Yes, yeah. But the damping it increases forever. Yeah, because then the poles are positive, and so your exponentials are increasing. But you don't want that. So, in order to describe the response, there are a number of characteristics we can look at, and these are all of interest to the user. So you may be asked to actually modify the inherent response of the system by putting a controller. So we can talk about, okay, what is the maximum overshoot of your signal? That's an important factor. In some systems, you don't want any overshoot at all, or minimal overshoot. Some systems can tolerate overshoot. The envelope in red, it tells you something about the decay, how quickly the ringing decay. You're interested in how quickly the response occurs, and that's related to the time to peak TP. And then the settling time, we measure, as we saw in the case for first order system, there are many definitions. Let's say that your definition is you want it to be within 5% final value, ringing, and when it starts ringing, the ringing amplitude gets less than 5%, the final value, we say, okay, it's settled down, and so that's the settling. So these are all characteristics you want to pin down in yours. And how do we control these things? They're controlled by the position of the pole. So the step response of a second order system is quite complex. There are a number of ways it gets represented. So you can have these exponential functions with cos and sine terms, or you can have a single cosine term with an exponential term, and you put in some phase change. So there could be a phase shift position of poles. So, in general, the solution, so you have an exponential term that's determined by the product of natural frequency damping factor, and this was our sigma d. Then you have an oscillation that depends on the natural frequency and the damping factor, and you have a phase shift. Okay, so one of the questions you're asked is, what is the percent overshoot? Now, the actual equation is messy, as you can imagine. This equation, trying to work out what's going on there is messy, but there are some good approximations. And so you have damping factor of 0.8, you get very little overshoot here. Damping factor of 0.7, now it starts to rise a bit, 0.5, and then there's significant overshoot, about 0.3. Yeah? So the equation, I won't go through mathematics, percentage overshoot can be approximate. So the overshoot depends pretty much on the damping factor. So the decay depends on the damping factor, and the overshoot depends on the settling time. Again, it's going to be messy, but this is a good approximation under the conditions stated there, and certainly this is the case. So the result is that in order to reduce the settling time, we need to increase the product both the damping factor. The peak time to get to peak. So time to get to the peak depends on this oscillation. So the higher the oscillation frequency, less time it takes to get. Sorry, that was the settling. No, that was the overshoot. Okay. The magnitude of the overshoot rise time, again, it's messy, but that's an approximation. So the result is rise time. So an approximation for rise time. Now, these approximations are quite useful. They help you understand what bits you can control and what happens where. All right? It's a bit like trying to control a squid, changing ones, they are interval. Okay, so we've already sort of looked at putting it in the S-plane, and so I've gone through. Okay, so if you have your poles and you move on the same axis, the 45-degree axis, then the change in response, this is time response here, and this is the S-plane. So if you're up here in the red, you've got a bit of overshoot. It's happening quite quickly because omega n is larger. As you reduce omega n, then you see that it takes quite a while. The amount of overshoot is pretty much the same, right? So this is keeping the maximum overshoot constant. If you keep moving along. We've already discussed doing this vertically, and so this is the case with keeping the settling time constant. So we can move up and down the vertical axis, keeping the settling time constant, so it gets within 5% of the final value at the same time. But you see that the amount of overshoot is different, and the time to the first peak is different. So by changing position along this axis, you change how quick the rise. But the downside is the settling time is the same. So if your critical design factor is the settling time, then you've got this freedom. And we've already discussed this. If you move them on a vertical axis. So you keep the maximum time to peak constant. So these are roughly the same time getting to the peak, but you can see that the settling time is quite. The blue one takes a long time to settle. The red one's quicker. And here's the case where you keep omega n constant and you move around. The circle radius is omega n, so you just move around on the circle. And all right, okay, any questions? All right, so our job is we want to come up with a process model. And the normal way you do it is, as I mentioned, the bump test, the step response. Now, from the step response, you can measure various things. So clearly, first order system, you want the time constant. You've got to work out a way of finding the time constant from the step. And if you know the time constant, you know where the pole is. And you now have a description of it. In a second order system, you have the right time to the first peak, you have the settling time, you have the oscillation frequency, you have the rate of decay. All those factors will tell you where poles are. So your job is to do bump test and then so in a first order system, we have a time response. So this is a first order system. So you sort of know what this one does, yeah? So this one has this sort of time. And so we can work out what our time constant is for the system. What do you think this? So this is a transfer function. So we've got a pole at 0 and we've got an exponential function. What is the exponential function? So if you go, to find out, how do you find out? You go to the Laplace and you just look it up. And if you look it up, you'll find that an exponential gives you, a delay. All right? So you give it a step response, and the response doesn't happen until So you might give it a step, kick the input, time t equals 0, might start to respond. And so there is a time actually respond. Yeah? And this is very common. So knowing how to model that is useful. There are many examples where you'll come across this time, like filling up a tank. So you've got a number of tanks, one feeds into another one. The second tank will not get fed until the first one is filled, and there's a delay. Right? You start the response in the first tank, you don't measure any response in the second tank until sometime later. Right? Or you can imagine that you have a pipe and you're putting hot water at one end of the pipe, and so you change the temperature of the input end, and you can guess that it will take some time before the output starts. So these cases of delay time. Another one is a valve. You may have an electric valve, and so you send out the signal to try and open up the valve, but most valves have some sort of slacken. So it takes a while for it to wind up before it actually starts moving the valve. Right? So again, there's another example. I have to model K. Now, Ks are bad. If you put them in a feedback system, then Ks are bad. What's the reason? It's all about not the error, no. So in a feedback system, we assume that the phase change rough pi. But if it becomes 360 feedback, now it's positive. So if you have a constant delay, at some frequency, that delay represents a phase change of 180. Add your feed, you've got 60 signals. So delays can cause oscillation. So there's a 3-parameter model, which is first order system with a delay. And another important model is this sort of S-shaped response. So we've got 2 poles, and they're identical, and this is critically damped. And we saw that gives you a linear time. And so you get this sort of S-type response. So it doesn't do the exponential, it starts to do this and again, you'll see that. And then 4-parameter model, you've got a time delay of L, and you've got 2 poles. So we sort of know how to handle that. So dead time, this is where the delay comes in. You probably heard the word dead time. Best example is the valve. They have a dead time. You send a signal to open the valve, take some direction. All right, so here's some example. I've already mentioned one. You have a system with some sort of cooling device. You've got hot water coming in and you're cooling it. Where you want the water is some other location. And because you've got a long pipe, the change in temperature of the input is going to take a while before it gets, so you get dead time. And so this is what without the exponential function, you have a step coming in at this time here, and you expect to have this exponential decay, but because you've got dead time, you've got a delay, so nothing happens until it gets to the end of the pipe. Another example is a very common example in chemical processing is you have some process in one tank, and the result of that is fed into another tank, and so on, and each one has to wait the previous one, so and so there's an equation for that, and so the end result looks like this. So you can guess, we can model this perhaps first order system with some delay. So the job is to identify what this have. So for first order system, we want to find this time constant t, and we want to find this delay. So basically your task is to do the fitting. There are basically you pick points on your exponential curve, take 2 points t1 and t2, and that'll give you something about how it rises, and then you sort of guess where this starts and everything. Right? So step response gives you a pretty good idea of how to model the system. And this is very simple. Right? So you measure T1, you measure T2, you know what the amplitude is, and you can out what it is as well. Yeah? Just plug in the number. Okay, so I'll give you an example, which is what's called a continuously stirred tank reactor. So it's described by this equation, and you end up having a step response like this. And this is what you use to fit your function. This is quite a complex description of your system, and under certain conditions you use this model. And so in pairing the actual system, I think the actual system is the dash line. Anyway, what this is trying to show is that the model is quite a good approximation to the system. Second order systems, we want to find out what the dynamic factor is, and so you can pick some points, take the values, and then you plug them into equations, all these factors are, right? And so I'm not going through that. There's an example. You've got a particular step response and you want to get a fit, so this is the response you're trying to fit, and so by going through the process you find out that that's the model for this system, right? Okay. Now, playing around with models, seeing their time response is something you want to get a feel for. And there is a website. All right, so this is the website. It's a group in Europe, and I've been using this for a while, but then last year it didn't work. So I wrote to ask them to grade it. But I just tried to install it here. So maybe he just graded the Mac. But it seems that the Windows version is for Windows 32. I don't know if it's on now. Well, this has been around a long time. So I had to change it to a bit Mac. I thought he'd do it. Anyway, you can go to modeling and you can play around with the different functions shown there. And please try this. Put in the system you have and see if you can get it to work, and let me know what happens. I think the Apple one worked. But if it doesn't work for Windows, let me know and I'll write them. And they were quite quick. I think they were chuffed at somebody over in Australia on my ways recently. Okay. So there are a couple of videos that you'll find useful. They only go up to first order. So A, B, and B is a very big industrial international company, and they have a number of videos which you find very useful. Sorry about that. Yeah, no, I don't think it's my voice.
This seems like your microphone voice.
Yeah.
So let's see what I think.
Hi, my name is Kevin Starr, and we're now on to Chapter 3 of the Single Loop Control Methods book. This is the chapter on process identification. This is where things start to happen. So I've got my sleeves rolled up, and we're...
I don't know how it's going. They're probably playing at my house. Sorry. Oh, it's still on there. Well, I don't know why it's going to be late. Anyway, you can look at that in your own. I don't know how to get it out of AirPlay.
We're ready to go because this is where tuning starts. There are several links in the chain that relate a process to optimization. They go through several phases, from modeling to PID models, or modes, There's standard, parallel, and classical are the three very general classifications. We're going to talk about that in a later chapter. And then we get into tuning. That's what everybody wants to get to. So tell me the magic rules, and we can get into whether it's Ziegler-Nichols or Pod A or Lambda or direct synthesis or overshoot or whatever you want. We can determine that in the tuning area. But you can't get to any of these steps if you skip process modeling, and that's what we're going to cover. In fact, this one is so in depth, we're going to break this chapter into 3 video sessions. There's going to be a session that deals with process transformations, how do we relate an input and an output. In other words, if you turn the steering wheel on your car, what happens? Is it fast? Is it short? You have to know that. Same thing with your process. But then what is the way that you identify it? How do you figure out what the dynamics of your process is? There's not you can't go to the pipe and look for what are your dynamics. It depends on so many different variables. There's Newton's laws of physics. There's all these different things that you can use. We're going to show you some very practical methods to be able to identify the process. Let it tell you what it is, and that's what we're going to talk about in this session. Then we'll go into self-regulating models, first order plus dead time. We'll talk about that. Then we'll get into non-self-regulating models. Those are tanks. Tanks are a lot different in terms of the type of model that we're dealing with, and we have to understand that there are 2 different types. If we represent
All right, choose Daddy Leisure. It goes for about half an hour, and I think you can change the speed. You can zip through this twice. I can't find the third one. So anyway, it's not relevant. We'll have a look at parts. All right, so now that we know how to describe second order class, we'll look at PI and PD systems, A1 and set characteristics. And then after that, we'll look at how do you play around coefficient behavior, and that's called tuning. So the process, if you want to control the system PID, first you've got to know what kind of system you're dealing with. Then you get a PID controller, you've got to play around with the proportionality constant, integration time, and the derivative. So there are 3 numbers you've got to dial in. Essentially, that's what it is. You're dialing in these numbers, and you're changing these numbers, you will get a system. Right? And dialing the numbers is the tuning. Now, that website that I pointed out, which an interactive website that didn't work, that has a whole bunch of other programs that they've written, and one of them is for PID. If you can get it to work, then we'll get that. All right, I think I've covered more than today. Any questions? All right, so we're getting to the point of real application. Right? So I'll see you on Thursday. Right?